My name is Shannon Bryant, and I'm currently a graduate student in Georgia Tech's online Masters of Computer Science program. Today's date is 6/30/2019, and I'll be presenting the paper Observing and Preventing Leakage in MapReduce, presented by Microsoft Research at Cambridge. Prior to discussing the contents of the paper, I'd like to acknowledge the authors Olga Ulrimenko, Christos Gansidis, Manuel Costa, Markul Kolvais, Cedric Fournay, and Divya Sharma from Microsoft Research and Carnegie Mellon University. This paper was first presented at the 22nd ACM SIGSAC conference in 2017, and there's a link provided if you'd like to view the original work. So let's discuss why this is relevant. Well, shared cloud infrastructure to process large data sets has grown significantly in recent years, exposing data leakage security concerns. During this presentation, I'll be discussing MapReduce processing and the secure hardware that a MapReduce job would run on, some adversaries that Microsoft Research has laid out as part of this study, how Microsoft Research intends for these adversaries to exploit MapReduce jobs. I'll be discussing some security objectives that Microsoft Research has brought into mind when implementing two Microsoft jobs, including Shuffle in the Middle and Shuffle and Balance. I'll be discussing the results of these two different MapReduce run implementations. And finally, I'll be summarizing their findings and relevance for this presentation. So what is MapReduce processing? Well, Apache Hadoop first developed MapReduce in 2011, and it is a model for processing large sets of data in parallel. If you look at the equations specified below, X is essentially your intermediate key value pairs. X is produced after the mapper phase once those key value pairs are generated. O is your output from the reducer phase. So after taking the key value inputs from the mapper phase, we run our processing in the reduce phase or the reduce function, and then pass output as for that batch record. To give you an example of how MapReduce process works, let's say that we wanted to determine the number of female residents residing in Georgia based off of the last census. So in batch 1, we would pass in the information for Georgia. In the mapper phase, we would take the gender column and assign either an M or an F key value depending on the row of data that we're evaluating. Once all that information has been aggregated, it can be passed off to a reducer function in another secure region. And in the reducer function, we would essentially take the value M or F. We can take all of the values associated with that and sum that information or count the information that's associated with that key value to give us an output of the number of female residents that are residing in Georgia based off of the last census. So I hope that gives you a better idea of how MapReduce process typically works. And now let's talk about some of the secure hardware that you would run a job like this on. Microsoft Research has defined a security hardware system as a system that stores data, intermediate key value pairs, and output data in an encrypted format and runs the map and reduce functions in secure regions. An example of a piece of hardware that Microsoft Research gave that can manage the sort of processing is VC3, and that's actually what they're using in this research study as well. To define secure regions, these are trusted and isolated containers of code that can be implemented as either physical or virtual machines. In this study, Microsoft Research is using Intel SGX processors as their secure regions to run both map and reduce functions. So now that we've kind of set up how MapReduce job works, the type of hardware that it runs on, let's discuss the adversaries that Microsoft Research has kept in mind throughout this research study. The first of which is a system-level adversary. And this is an adversary that doesn't have information or background knowledge about the job that's being executed, its inputs or outputs. This type of adversary can monitor network traffic or storage traffic to determine the volume of data actually being exchanged. So an example of an application of this is when in a reduce phase, you could send information or transactions to a database. So when you're reading and writing from another cloud database storage center, that information can be monitored, which can essentially lead the adversary to determine information about the volume of data that's being inputted or processed in each of the phases, leading them to determine input information later on. An adversary at the system level can control resources and scheduling of MapReduce jobs. So essentially they can either pad extra input information to see how it looks in the map in the intermediate phase and the output phase, or they can rerun these MapReduce jobs to get a better understanding of the type of volume that's being run on that data set. The second type of adversary is an application level adversary. And conversely to a system level adversary, this type of adversary has knowledge about the MapReduce job being executed, its inputs, and its outputs. This information can essentially be obtained from traffic monitoring. So as specified before, if you have no information, you have system level access, you can obtain this information from traffic monitoring. It can be obtained from common knowledge. So let's say that the intermediate key value pairs denote that it's pulling from census information. Well, some of that information is publicly available, so you're able to ascertain information about the inputs and outputs that would be performed on that MapReduce job. Additionally, you can use data exchange profiles, binary code size, and runtimes to determine some of this information. So let's discuss what intermediate traffic is. If you remember in the first diagram how I had the value X, which stands for intermediate values, intermediate traffic is essentially monitoring this information between the map and the reduced stage. And it's specifically observing key value pairs being passed from the map to the reduced stage, resulting in a matrix A. So this diagram down in the bottom, if you look at row 1, this would essentially stand for the key, and it has values 3, 0, and 0. Column 2, or row 2 has values 1, 1, and 1. So this is after those key and value pairs have been generated in the map stage and have been encrypted and sent to the reduced stage. We can monitor that information while watching the network traffic for this job. To exploit this information, there's a type of attack called a job composition attack that essentially occurs when an adversary observes traffic from more than one job and where the same input data is being used to exploit input values. One of the examples that the paper gave was observing census data being run through multiple MapReduce jobs where they were processing aggregate information for zip code, gender, and date of birth. If you combine all of this information and they share a key value, you can uniquely identify individuals in this case. So now that we've discussed how to use intermediate traffic to essentially exploit information about MapReduce inputs, there are two different types of specific exploits that can be run using this type of method. The first of which is an individual record exploit, and as its namesake portrays, it's used to determine information about one record, one person, one instance. An adversary must know input data from a data set. One of the examples that was given in the paper was if an adversary knows the pickup time and pickup location of a taxi rider in New York City, they can determine the drop-off location. That is if the adversary knows that the input data is taxi information that's being passed in as the data for that MapReduce job. The second type of exploit is a batch record exploit, and this is essentially used to determine output for a larger population. And again, the adversary must have some information about the intermediate values and output data that's being presented at a MapReduce job. One of the examples that was given is if an adversary knows the aggregate counts by state of where people work and where they were born, then they can determine the distribution of birthplaces for Georgia residents. So prior to diving into the two MapReduce implementations that cover some of the security concerns that we need to discuss, they define this as a MapReduce game. And this is essentially where we take the adversary that we outlined previously. We either have a system level or an application level adversary that is able to view traffic from two data sets. And we're assuming that those two data sets, the traffic looks the exact same. Will they be able to determine which job is processing which data set? So this is what we're trying to protect against. The first security definition or thing that we're going to be building for in our MapReduce implementations is correlation hiding. And this essentially accounts for the fact that the adversary only observes encrypted keys, hiding which records have common keys, preventing a composition attack. If you remember my example of a composition attack a couple slides back, this is when you have information about someone's gender, place of birth, etc. And because they share the same key value, you can determine who that person actually is. So this type of security measure will help prevent against those kind of attacks. For strong hiding, This essentially dictates that the volume of intermediate data is the same, the number of records for the most popular key is the same, and the reduce output size is constant. So by making that network traffic appear to be similar, and by padding that most popular key with dummy values to get it up to a certain size, you really can't distinguish between two data sets. So this is very important for when they're viewing that intermediate traffic, they really can't determine which key value would have more or less values. So the first implementation, it was called Shuffle in the Middle, and of this job, it essentially shuffles data between the map and the reduce stages using a permutation. So to give you an example of how this would work, you get a batch of information, it goes into your mapper function, it produces key value pairs. That information is passed into a shuffle phase, and what it does is it essentially shuffles where the values are going to be reduced, where that reduce function is actually going to run. And that allows you to not only prevent that key value pair from being traced back to a mapper, it also prevents you from knowing which value is associated with which key. So very important there. And this implements correlation hiding by obscuring which mapper function, as stated previously, produced the input data for the reducer. The second implementation is called Shuffle and Balance. What this does is it shuffles prior to the map stage offline, again using a permutation. So what this does is this actually prevents against any filtering attacks. So in the previous definition, the shuffle was happening in between the map and the reduce phases. Since the shuffle is happening at the beginning, we really can't tell if that information's been filtered. We really don't know, anything about it. An adversary cannot ascertain any information about what's being passed into the map stage if we shuffle prior to passing it into the map stage. Once that information is passed into the map stage, we're actually padding those values with key value pairs, so essentially adding more information to it. And we're using bin packing to ensure that we're using the same amount of reducers, as well as making sure that the values cannot be traced back to keys, and those intermediate values cannot be traced back to a specific mapper. This implements the strong hiding security definition, again by obscuring volumes of data, so we really can't tell if this is dataset 1, dataset 2, dataset 3, because we are using bin packing and padding intermediately between the mapper and the reducer functions. So now that I've discussed how Microsoft Research has implemented Shuffle in the Middle and Shuffle and Balance, let's talk about the results of their findings. Well, Shuffle and Balance ended up outperforming Shuffle in the Middle due to the offline pre-mapped shuffling phase. The research team essentially ran information for the taxi data for New York City in 2013 and the 1990 US Census data to run both aggregate processes and aggregate filtered processes, so filtering that information prior to the map stage. If you look at table 2 and look at that last row, pass in -1, this is the aggregate function that was run using the shuffle and balance method. If you look at row 1 in table 1, census age grouped, that is the aggregate function that was run using the shuffle in the middle phase. And then if you look over at the runtime over in the far right-hand column for both, you'll notice that the runtime was significantly less for the shuffle and balance implementation, displaying that this is actually more optimal when you are running your MapReduce jobs in a cloud setting. In addition to being a more optimized implementation of MapReduce, it implements a more robust security controls by preventing adversaries from detecting data volume through traffic analysis, as mentioned previously, by padding some of the traffic that's sent between the mapper and the reducer functions, and utilizing bin packing so that the same amount of reducers are used in each job regardless of the amount of data that's present. So now that we've discussed what MapReduce is, the different implementations that Microsoft Research has done to try and protect against some of these leakage concerns, let's kind of summarize the presentation and conclude. So firstly, MapReduce leakage is an important security concern as companies continue to utilize public cloud infrastructure to process big data. Adversaries can observe network or storage traffic of MapReduce jobs and infer information about the input data based on intermediate values by performing job composition attacks to either exploit individual records or batch records. In order to protect against MapReduce jobs, Microsoft research has proven that the strong hiding security principle is recommended to obscure data volumes, preventing adversaries from deciphering input values. So essentially preventing against filtering attacks at the beginning or those job composition attacks where intermediate values can be defined between the map and the reduce phase. Also, organizations can leverage offline shuffling using the Melbourne shuffle algorithm, padding and bin packing to obscure data volume. Thank you so much for your time, and I hope this presentation was beneficial for learning about MapReduce and some of the leakage concerns that are present in today's public cloud infrastructure.